Okay, so this is question number 13 of the nuclear physics homework booklet, and in question number 13 we are told that the age of an ancient boat can be determined by comparing the radioactive decay of carbon-14 from living wood with that of wood taken from the boat. We're told that a sample of 3 times 10 to the 23 atoms of carbon is removed for investigation. So we've got 3 times 10 to the 3 times 10 to the 23 atoms to work with. And that comes from a block of living wood. And we're told that in living wood, 1 in every 10 to the 12 of the carbon atoms is a radioactive isotope of carbon-14. So we've got all these particles all together, all these nuclei all together, but only 1 in 10 to the 12 of those is actually going to be the radioactive isotope. The rest of them are going to be carbon-12, which isn't radioactive. And then we're told that carbon-14 has got a decay constant of 3.84 times 10 to the minus 12 per second. Okay, so in part A, we're simply asked what is meant by the decay constant. This is a definition that you just need to learn. So the decay constant is the probability of decay per unit time. That's it. Don't try your best not to say per second, actually say per unit time. It's a better definition. But if you write that down, you get 1 mark. We're then asked to calculate the half-life of these carbon-14 atoms in years. And we need to focus on this because we're asked to give our answer to the correct or an appropriate number of significant figures. Well, if we look in the question, every single one of these, every single number we've got, well, to be fair, we've only got 2, is to 3 significant figures. So that's what we're going to give our final answer to. Now, if we're going to calculate the half-life, the only way we can do that is either from a graph or from the decay constant. The decay constant we're given, so we're going to use that. So the half-life is equal to the natural log of 2 over lambda. Lambda we're given here in per second. So if we put it into this equation, this tells us what the half-life is in seconds. We don't want it in seconds, we want it in years. But helpfully, they tell us how many seconds are in a year. So if we simply take the number we've got, if we divide it by the number of seconds in 1 year, that'll work out we'll be able to work out how many years that is. And if we do that, we get 5,730.158. So to our 3 significant figures that are in the question, that gives us 5,730 years. In part C, we're then asked to show, so this is one of those things where we basically have to come up with this number. We have to show that the rate of decay of these carbon-14 atoms in the living wood is 1.15 becquerel. In other words, we have to use this equation here. This is the only equation that we can use in order to calculate the rate of decay. Now the exam board are a little bit, sometimes they include the minus sign, sometimes they don't. I have here, if you do include the minus sign, it doesn't matter, then it's absolutely fine. So the rate of decay, so this rate of decrease is equal to minus the decay constant multiplied by the number of atoms. Now the number of atoms, you've got to be a little bit careful because this is the total number of atoms we've got, but we're told that only 1 in 10 to the 12 of those is actually a carbon-14 atom or carbon-14 nucleus. So we need to take all of these. If we divide it by 10 to the 12, then that'll tell us how many atoms of carbon-14 we've got. And if we do that, we get 3.00 times 10 to the 11. So that's the number of, this is our n here, that's the number of carbon-14 atoms we've got. So then we simply have to put our numbers into our equation. So this is the rate of decay. This is the decay constant from the question. This is the number we've just worked out. And if we put that into our calculator, we get a rate of decay of minus 1.15 becquerel. So ignoring the minus sign, basically we've answered the question. In terms of marking points, you basically get 1 mark for using this equation, putting the numbers in, 1 mark for actually showing that this bit then gives you the right answer. In part D, we're then told that this sample, the same sample of wood, or the sample of wood from the ancient boat with the same number of atoms is taken, and that the rate of decay due to carbon-14 atoms is 0.65 becquerel. We're asked to calculate the age of this boat in years. So, what we know is we know that this is the rate of decay or the activity in living wood. This is the rate of decay or the activity in the really old wood. So basically what we can assume is that sometime in the past, just as the tree was cut down, the activity was this. So that's our starting activity. It then decays, so all of these carbon-14 atoms then decay, so the activity goes down, and it's gone down to this number here now. So what we can do is, if we use this equation here, so we've got our activity is our starting activity multiplied by the exponential of minus lambda t. Our starting activity was the 1.15 becquerel that we worked out in the previous part of the question. The activity now is 0.65 becquerel. This lambda is the decay constant that we worked out in years, which was up here. Sorry, it's the decay constant that we're given up here. And then finally, the t is what we want to calculate. So if we put these numbers into our equation, we've got 0.65 is equal to 1.15 e to the minus lambda t. Rearrange this so we've got the exponential just on its own. Take natural logs of both sides, and that gives us this. Rearrange this, and we get t is equal to minus 1 over the decay constant multiplied by the natural log of this here. And if we simply do that on our calculator, we get 1.48 times 10 to the 11 seconds. We don't want it in seconds. We've worked our answer out, but we want it in years. So we go back up here, up to here, and we take this conversion rate again. So we know that 1 year is 3.15 times 10 to the 7 seconds. We divide our answer that we got here in seconds by the number of seconds in 1 year. That tells us how many years it is altogether. So to 3 significant figures, this piece of wood is 4,720 years old. Now finally, we're asked to simply give 2 reasons. So all we have to do is write 2 reasons down. Why it's difficult to obtain a reliable age of the boat. So it's not about thinking about the age of the wood, it's thinking about the age of the boat. So for example, the boat might have been made at some point later than the tree was cut down. So maybe the tree was cut down and or the tree had fallen over or whatever, and it was there for a long time before the boat was made. Also, the count rates are really low. So actually, because the count rates are low, it's very difficult to tell the difference from potentially background radiation. The uncertainties are going to be really quite big. Alternatively, the amount of carbon-14 in the atmosphere in the past could have been different to what it is now, because what we're assuming is that the activity now was the same as it was when it first started a long time ago. It could have been different. So that's another reason. Basically, you just need to write down 2 of those and you get both marks. So that was question number 13 of the Nuclear Physics Homework Booklet.